Good morning, everyone. This is Alan Tsai. I'm the Principal Wireless System Engineer in Security Engineering. Today's webinar topic is 5G map-based channel model simulation with network simulator. We also will share more information about our network simulator. This will be our future product release next year. This network simulator allows users to define their use case and scenario. It can be LTE, Wi-Fi, or millimeter wave, and their scenario can be indoor, outdoor, or like highway or urban area. And this network, and you can choose your own antenna, like customer antenna or like offshore antenna, and we will predict the data rate, throughput, and power consumption. Before we go more deep, I want to have a quick introduction about our company. We are based in Oakland, California. We are ANSYS certified channel partner, which means we provide all the ANSYS softwares, and which including structural magnetics, fluid dynamics, electromagnetics, and particle. And we help our customer do consulting of software's technical support and training and partnership. If you are based in Bay Area and you have any simulation problem, please contact us. We're happy to figure out a way to help you. And so today's webinar have 3 parts. Part 1 is LTE system data rate prediction, and part 2 will be Wi-Fi data rate prediction and power consumption. And part 3, we will use map-based channel model in Wi-Fi system to predict the data rate and the power consumption. Today, we want to send in one message. Is your antenna good enough for your product? Do you have enough data rate? Is the power consumption acceptable? Here is the key antenna design parameters: frequency, bandwidth, impedance, antenna efficiency, directivity, antenna gain, radiation pattern. But how those design parameters will affect to my data rate and power consumption? Which one should I change to make it work? Here is our solution by using our network simulator. First, you got your antenna pattern from your own design or offshore antenna. Second, you define the scenario. It can be indoor, outdoor, highway, or urban area. And third, you can choose like which type of simulator. They can be IoT, Wi-Fi, 5G, LTE, or car-to-car communication. And they will produce like performance prediction. They can be throughput, power consumption, and etc. Here is today's scenario. It's a single cell base station and one user. The case 1, we using isotropic antenna. Everything is very ideal. Case 2, we use realistic antenna pattern from ANSYS HFSS. And we will simulation more detail about the PCB board and the material of antenna and etc. And we also put a human head and hand near the cell phone. Here is a key value of our network simulator. Figure 1 is distant burst throughput in different scenarios. Shows like each type of antenna's data rate in different cases, so we can compare which one is better easily. Figure 2 is a throughput vs MCS. So we can know how many antenna gain is needed to achieve higher modulation order to get a higher data rate. With these two figures, we can know this antenna is good enough for our product or not. If it's not, we have better understanding how to improve antenna to reach our goal. In part 2, we are going to talk about Wi-Fi system data rate prediction and power consumption. In this scenario, we will have an AP, which can be a router we set up in the central, and the height will be like 0.5 meter. And we have a UE, that in this scenario it will be a cell phone. And each second, the cell phone will step 1 meter away from the router. And in this scenario, we will try to reach maximum throughput. And we are using Wi-Fi protocol, IEEE 802.11g. And here you can see they have like compare with two kind of antenna. One is isotropic antenna, which is very ideal. It's like a ball, and it will be 1 dB. And another one is like our antenna from HFS. And you can see here, our antenna have better performance, so they can even have a more far away the distance, they still have better throughput. They still can reach like 27. And in this scenario, we try to use a single antenna case. Yeah. Okay. And the second one, this one, we are curious about power consumption. So you can see here, it's still the same scenario, but the UE have different power level, and they will try to try to reach certain of the throughput, but try to save power as many as they can. So you can see here, the HFS antenna still have better performance, but they was going down to reach the same, but try to save more power. So here, this in the right chart, right figure, you can see like each second, when they go more far away, the isotropic antenna need to spend more power to reach the same data rate. So in this two chart, user can easily to choose which antenna can reach their minimal criteria, but still can save power. And we know this is very important, especially for IoT devices, because you don't want to change battery very often. Also for those drone, if the drone you need to charge it, there will be a big trouble. Also, but for those drone, like if they have streaming, they also very care about the data rate. So they definitely have a trade-off. And to find like the best antenna to fit your product, we hope our network simulator can give some variable like value. In part 3, we are going to discussion about 5G main-based channel model, data rate prediction, and power consumption. And first, we will talk about how to generation main-based channel model. And we were going to use ANSYS HFSS tool, and this is a ray tracing simulation tool, and we will have a quick demo. Okay, this is HFSS, and so first I will show like how to use it, and second I will tell more about how to generation map-based channel model. And you can see here, this is our office, how it look like exactly, and they have like a wall, and have floor, and I put 2 antenna, 1 router and 1 receiver, and let me take out the seal, so easy to take a look. And here you can set a different like material, and also you can put like a different color. So sorry, add index, and so you can easy to tell looks different. And let me put maybe another color, and it would be still blank 5. You can click. So now it will be easier to tell. Sorry. Okay. So we have a floor and have the wall, and this is our router, and we choose dipole antenna, but they can switch to different kind of antenna, and they can even have a bin, and also you can like import from HFS file. And to try to keep simple, this one I use dipole for both router and cell phone. And this is our cell phone. And we set up the router at 0.5 because it's like our table's height. And this is the cell phone. We assume that people is holding hand is kind of 1 meter. And you can also set up different like material like PEC, like perfect electro conductor, and also like observer, perfect observer. And here it's the analysis, and you can have a different mode. One is like the far field, near field, and today we choose antenna to antenna coupling, and we set that router be our transmitter and cell phone be our receiver, and this is cell phone antenna. And they have a different way to run. Oh, so we set up the frequencies at 2.4, and how many bounce. Because this is ray tracing technology, so this is define the density of the ray and how many bouncing you want. Because I have a wall, I have a bouncing, and this is output file, and we need like the full field and touchstone file. Total field. So total field is it's including like path loss and scattering. And scattering is caused by the wall because they have multi-pass, and here today is like we use like this one is the multi-run sequence. So you can put a variable, and I use this like I take the cell phone one to here, and so I can choose like the cell phone position I want change, and this is the list. So you can see each run like the cell phone or location will be different. They will move far away from the router. And after running simulation, they will store here, and which one? 10. So it's a little slow. And you can click, and they will have all the result here. Show like the loss of each point, and we will take out this result and to process put inside our network simulator, and we will predict through data rate and power consumption. And also this one also have another function. You see here, this is like a virtual ray trace. So if you set up a range from the transmitter, in this case will be like our router, and you can see they will have a shooting ray, and you can set up how many bounce you want. Maybe your benchmark 2, so this will just 2 bounce, and if you set up more, you can see more bouncing, and you can have the density, length, and statistic, how many bounce they have. Yeah. So we use Savan. Now after running, we can take the file. So after running, then you can go to sequence and you can find out like every simulation result stored here, and this have the, you can open it, and they will record like the frequency and like the real image part, and like all the path loss will store here. And they have, you need to go through like different file. And so we write a Python script to read all the file and create a table, and we will feed in our network simulator, and we can run simulation, and we can get the data rate and power consumption. Okay, so here is our Python script. So this will help us, they have two purposes. First, this will help us to generation like the multi-sequence stuff I need to run, so we don't need to type this one by one. And after running simulation, we use a Python script to read and calculate like the path loss. So in here you can see this one will be X and Y, Z, and this will be like the dB loss. And so this will be like each location's the dB loss. And if you have run multiple location, then there will be a map, and this will be our MAP-based channel model. And we just need to feed this table inside our network simulator, then we can have run simulation. After we use Savan to run each location's ray tracing simulation to get the path loss of each location, we can use Python script to get those data and do post-processing to get each location's path loss in dB, and they will be a part of information of our main-based channel model, and we feed those information inside our network simulator. After that, we can predict data rate and power consumption. And here is the one scenario, and we have one user in one AP, which will be a router in the central, and the height at 0.5 meter, and another will be a receiver device, will be a cell phone, and this one will move around, and the height also is at 1 meter. And because this is a free space, so we will try to compare with two-ray ground propagation loss model, and the number is pretty close. Two-ray ground propagation loss model, here is the expression. It's very good for its free space and just left side and the one bounce from the ground. And here is the simulation result. In this scenario, we have like two type of radiation pattern. One is like a cell phone antenna, like the one we have in LTE, but also have Wi-Fi antenna. And it's the same cell phone, and we put a copper plate next to it, and to reduce the antenna gain. And you'll see here, with the copper plate one, the throughput definitely, like, you can see a drop, like a significant drop in 75 meter, but without a copper plate, the drop is like 110 or almost 120. So here you can see almost like 40 meters improve, like better than each other. Here is also see the power. And you can see like if antenna next to a copper plate, they need to use more power to transmit. And so like if this area will be the energy they use, because this is the time, this is power, so this area actually is the energy, total energy they use. And without the copper or any like metal plant, actually antenna have better performance. And this is like mm, same as our common sense. And let's see another one, another scenario. So this scenario, we use our office like 3D geometry, and with the material is a plank for like a wall and floor and the seal. And this one will be our cell phone, and this will be our router, and cell phone will move around. And we run like ray tracing, and because they have a wall and this have the bouncing, so actually it's you cannot use like two-ray or any equation to get exactly like a right channel model. You need to use like you need to import 3D geometry. So like use after like a Savant, this kind of tool, and import 3D geometry and use ray tracing to get like a more accuracy channel model. And this will be more important when it's happening in millimeter wave, because in millimeter wave, when the frequency is high, like the path loss is huge and you don't have enough multipass. So it's difficult to use like equation to predict when it's high frequency. Only like use ray tracing and have like a real world environment information inside. At least you definitely need to consider the real world environment. So it's you can imagine that like if you use equation, you just input like a distance, frequency, and maybe some probability like shadowing. But like in the real world, if they have a huge wall in front of you, and the wall is a metal or it's like glass wall, it will be very different. The result will be different. And also it's like when it's a 60 gigahertz, like even maybe like a human body can just block your signal. So you're not sure which one you have like the huge like receiver, which angle you will have like huge and enough, not huge, like enough like path loss, not too huge. Okay, let's see the result. And you will see like the blue one is a cell phone, and the orange one is a cell phone with a copper plate. And in this experiment, we want to show like if like we know like if I have a copper plate, they will reduce the performance, but we don't know how much reduce if it's in like a room environment like our office. So you can see a result like if I have a copper, but still in like the two ray or like the free place, it's like when a certain point it's got zero. But in the office one, because I think because those walls still have chance to bounce, so in certain distance they have chance to got like still got a signal because the bouncing. So this is like ray tracing, like those real world like geometry environment can information can provide. You don't before like if we don't run simulation, we don't expect after like certain distance they still have chance to receive, because like the bouncing we don't know which angle exactly they will bounce. And we see like here it's the power, and it's a kind of makes sense. It's like the blue one still use a little less, but they don't have much difference. But you also can compare with these two. You see here, in the general, like without any like war, they can use less power and have better performance. But after if we have put like our office real geometry and the environment setup inside, and they actually have like they need to spend more power to get like the performance not even like better than before. Yeah, and so uh, we think like if it's go to 5G, like especially high frequency real world information will be provide more like hidden like variable information inside. Yeah. Okay. And here it's like just to summary like our network simulator, and also like introduce some of the input parameter you can input in network simulator. They still have much more, but I just pick few. It's more common and useful. First, you can input your antenna radiation pattern. This one can get from simulation tool like HFSS, or you can use your test result. And second, you can decide like what kind of like protocol you are going to use. You can use Wi-Fi, LTE, or millimeter wave. And the third one is the channel model. You can use like a ray tracing, like use subband to get a ray tracing map-based channel model with real world geometry information, or you can use the channel model like a two-ray or log or other. I have multi different like channel model with like math equation and probability. And second is like a frequency number. So it's mean like which frequency you use and how many frequency band you are using. And in the LTE and Wi-Fi protocol, they have like specific to have a table to tell like user which channel number you use is mean like which frequency and how many frequency band you can use, and how many frequency bandwidth you can use. And the last one is also another one since have a huge potential. It's like this network simulator can run multi-user. In some scenario, like most of the time, the link budget is not just like a passload they have, because they have like other user cause interference, so make you don't have a good quality channel, because other people also sending signal and they will cause you interference. And we can simulate that. We can put like multi-user inside network simulator, and we can predict like what kind of interference they will cause and will affect to our data rate and power consumption. And the last one, like of course, you can set up your devices, like either it's like a router or your receiving device. It can be a cell phone or drone or any like smart home IoT devices. And the power is important because you can, if you use like high power, you might have chance to get a better channel quality, but also you will use more power, your battery will die faster. Also, you might cause other people's interference. So after you decide which kind of parameter you want to to define, or you can use the default one, and you can fit in our network simulator and choose the scenario, and we will predict the data rate and power consumption. And we just finished this prototype, and now we are currently doing validation. So if your company have some product you want to test in, you can like connect to us. Maybe you can share some information like antenna radiation pattern and what kind of protocol you are using, and we can send you back the data rate and power consumption. Also, if they have a more like system level information you are interested to know, you also can connect to us. So maybe we can provide more detailed information. Okay, thank you so much. Thank you for your participation. And this will be our last webinar in this year. If you have any question or advice, please reach to through our website or LinkedIn or email. And wish you guys Merry Christmas and Happy New Year.